This is a lesson on polarity. Polarity means a uneven distribution of charge. Central concept of this is electronegativity. If you look at electronegativity, it is the relative ability to attract bonding electrons. It's kind of like electron affinity, but it's just electron affinity is energy when an atom actually absorbs an entire electron. This is covalently bonding. It's the relative ability to attract the bonding electrons. In general, small atoms have a high electronegativity. The noble gases don't count because they don't have any bonding electrons. Therefore, fluorine is the highest. Now, before it says the relative ability, relative is compared from one to another. So they set fluorine, it could have been 10, could have been 100. They set a fluorine at a perfect 4.0, like GPa. In the opposite corner, francium, I think it's something like 0.6. So that's the range of things, and I guess the noble gases have zeros. So this is the concept of electronegativity, the relative ability to attract bonding electrons. We're going to use this to determine whether a bond is polar or not. So on polar bonds, the electron is not shared equally. We've talked about this before. And what you do is you subtract the electronegativities of the two atoms in the bond. So you subtract the two electronegativities, the larger one minus the smaller one. If you get a negative, make an absolute value. No negatives, please. And it runs like this. If it is between 0 and 0.4, it is nonpolar covalent. If it is between 0.4 and 2, not including 0.4 or 2, it is polar covalent. And if it's between 2 and 4, then it's ionic. These are arbitrary numbers. 0.4 is a cutoff. It could be 0.3, it could be 0.5. No specific reason for that. It's like a passing grade. Sometimes it's 70%, sometimes it's 60%. It's just whatever. They pick a number, it sounds good, and they go with it. And there's not a large changeover. It's not like there's a big gap between nonpolar covalent and polar covalent. The difference between 0.4 and 0.5 isn't like night and day. And this is different shades of gray. It's like going from daylight to nighttime. It just gets gradually darker and darker and darker. Same thing here. The change in how the electron is attracted gradually shifts from one to another. if this is the nucleus, this is the nucleus. If it's nonpolar covalent, the average of the electron cloud is in the middle somewhere. If it's polar covalent, it would be more towards one side or the other. And if it's ionic, the average would be on the nucleus itself. So this would be nonpolar covalent, polar covalent, and ionic. So it sends the shifting electron cloud gradually from the middle to one side or the other. These electronegativities are found on page 184 in your textbook. Example, HBr. H is 2.1. There's no units on it, it's just a relative number. And Br is 2.8. So you take 2.1 minus 2.8, rather 2.8 minus 2.1, and you get 0.7, which makes it in the polar covalent range. The 2.8 means it's more negative than the 2.1, so you can make a Greek letter D, lowercase d, that's delta, and it's more negative on this side. Then this side would be partially positive. If it was switched around, then it would be the other way around. So this is how you do that. Suppose you had something like, fluorine, 4.0 minus 4.0, 0, which is non-polar covalent. And say you had sodium chloride, salt, which is definitely ionic. Sodium is 0.9, chlorine is 3.5, subtract those, you get 2.6, which is definitely in the ionic range. Up to this point, we've been talking about bonds between two atoms. Now we're going to talk about the entire molecule. The polar molecule are caused by lopsided electron clouds that come from asymmetrical, or not the same, an asymmetrical molecule. If you rotate the molecule, if you check the molecule for symmetry, that means you can rotate it through one bond angle, rotate the atom through one bond angle. So you got to check the geometry. Which means the rotation things goes the same. And you also got to check the polarity of the bonds. Generally, this means if you have a different atom, different atoms have different electronegativities. Therefore, if you have 3 atoms of one type and one of the other, that'd be asymmetrical too. Now, doing Lewis dot diagrams, it's not really a bond angle of, let's say you have X. It's not really a bond angle of 109.5 like it's supposed to be with tetrahedral, but 90 degrees. It's drawn that way. In real life, it's going through 109.5, but for our purposes here, it's got to be 90 degrees so you can see what happens. So if you rotate the entire molecule clockwise or counterclockwise 90 degrees, you'll notice that each H falls on another H, so this would be symmetrical, so it's non-polar. No change, non-polar. If it had a lone pair, that lone pair still counts and still rotating 90 degrees. In this case, the lone pair will be kicking out a bonding pair, and a bonding pair will be kicking out a lone pair. This would be a polar molecule. Same deal here. It's still 90 degrees because you're attached to four things. So if you do that, it's going to be polar also. General statement, true 99% of the time. If you have a lone pair on the central atom, it will be a polar molecule. If you have a trigonoplanar with a double bond, you rotate that through 120 degrees, and the double bond replaces the single bond replaces the double bond, and it changes. So that would be polar also. Generalization, if you have one multiple bond on the central atom, if you have a double bond, or if you have one double bond or one triple bond, what you got is a big giant electron cloud out here, even if it is between two other atoms. You've still got a giant electron cloud over here, and it's still lopsided. And then the last ones are the linear molecules. If you have a triple bond, again, if there's a triple bond on the central atom, now the bond angle is 180 degrees, and if you flip-flop that around, you notice that the triple bond kicks out the double, or single trips up. Start over. The triple kicks out the single, and the single kicks out the triple. So it is polar. And the last one is linear with two double bonds. Now in this case, it's still 180 degrees. If you rotate this through, it could be polar, it could be non-polar, depending upon what you have at either end. In this case, it would be non-polar, or polar, sorry, no change. Yes, there is a change. If it was C and C, then it would be non-polar. So pretty much it has to be a tetrahedral with all of the atoms the same, or a double bond, two double bonds with the same element on both sides to become non-polar. Pretty much everything else is polar. That ends this little lesson on polarity.